Thanks, everyone. I'll try to get through this on time. I'm not going to be like a normal academic and ramble on too quickly. So I have an alarm on my watch to stop me when I'm ready to. So let me just come right out and say, like, why should you listen to this talk? Why do you care? This is sort of the essential bits in the first slide. So we in my lab have developed a new, very modular approach to probing defects that we call broadband cryogenic transient dielectric spectroscopy, which is a bit of a mouthful, but it's sort of representative of all of the good bits that we want to highlight. So this is mostly targeting two-level system defects and superconducting materials, which I'll talk about as an introduction in the next few slides. But what I'm really excited about giving this talk to this audience in particular is I'm really looking for partners to provide materials to us. If you're curious about defects in the relevant ranges that we're talking about, particularly like semiconducting materials and other types of devices, I really want to expand this technique out to other materials. And sort of bonus points are if you understand the defects well, it would be really nice to sort of corroborate our approach as sort of a proxy for these other techniques where, say you really understand your defects well in your system, we could measure them in our technique and ideally provide complementary information. So quick overview of what I'm going to talk about. I'll sort of do a little bit of a dive into the particular defects we're concerned about and why in superconducting circuits, talk about why it's important that we're studying this in a very broadband environment and how we can identify individual defects by their spectral response, and then provide a conclusion and outlook and hopefully stimulate some questions. So this is a little bit of a historical perspective on two-level system defects. This goes back to really the 1970s when people were studying, in particular, glassy or amorphous materials at very low temperatures. This is kind of fun. I'm still on the younger side, so you know, these kind of plots are not as familiar to me, but I'm learning to appreciate them. So this is a plot of temperature on the x-axis, and now what you're looking at is specific heat, but you're sort of scaling it by temperature to the third power, which is what you'd expect from sort of a phonon occupation. And you see these funny little bumps that happen especially for amorphous materials. And so the question is, what's going on at these low temperatures, and why do we sort of lose the nice temperature to the third scaling of the specific heat capacity? This was very quickly addressed by several people, and in sort of classic physicist form, it was we built a very, very simple toy model, which is this two-level system model. It's basically a double well potential where you can have some asymmetry and there's some tunneling barrier V. Now, this is a mathematical model that you can use to study, and it really nicely captures these sort of bumps in the specific heat capacity, but it's more of a mathematical object. And as I'll talk about in a little bit, we don't really know how to go from an atomistic structure of these materials to an effective model like this. That's one of the open questions we hope to address with our technique. So here's kind of a fancier new version of that from our paper. So superconducting circuits, still a relatively new field, but there's been a lot of progress, particularly from a quantum computing standpoint. Now, this is a plot as a function of year, the lifetime of different qubits reported in the literature. This is kind of commonly called Shulkoff's law, for Rob Shulkoff, who's really driven a lot of this innovation. And we've seen a lot of steady progress, but most of this progress, I would say, comes down to designing different parameter regimes of these quantum circuits. So there's a whole zoo of different types of superconducting circuits, and a lot of the engineering that's been done has been focused on like, how do you trade off, how do you design the parameters of these circuits, in particular the charging energy, the Josephson junction energy, and a sort of inductive energy, to change matrix elements and couplings to lossy interfaces and things like that. I guess the high level thing here is that this is mostly on the engineering of the circuit architecture. It's not on the materials engineering, and that's really what I want to focus in on. So one of the sort of essential things that kicked off this whole study of revitalizing this two-level system defect model in superconducting circuits is, one, well, we operate at cryogenic temperatures, so these defects are known to populate at these temperatures and are not thermally washed out. But as you can see on the left, like, this is an older style XMON transmon qubit. The Josephson junctions, the essential sort of nonlinear element, sits here. These today are still mostly formed from aluminum, aluminum oxide, aluminum Josephson junctions, particularly because they're easy to manufacture. We can do directional evaporation of aluminum, grow a native oxide in a vacuum chamber, and deposit the top layer. But as we'll see, these things are riddled with these two-level system defects. But as you can see in this plot, there are a lot of places on a chip where these defects could arise, and I think there's still not a very clear consensus in the field as to what they are from a microscopic standpoint. You know, they could be hydrogen atoms, they could be adsorbates, they could be sort of, you know, atomic configurations that are approximately the same energy, and you get a tunneling process between them. It could be junk on the chip or structural damage. No one really knows. But what we do know, and why it's consistent with the defect model, is that you can tune them with mechanical strain or a DC voltage, and you get these nice parabolic arcs that are consistent with the two-level system model. Now, these are a big problem. So as Fahad mentioned, I worked at IBM Q before starting my faculty career, and I worked on large scale. Now, this is large scale for the time. It's getting much larger now. But when you look at the coherence times, the relevant figure of merit for these devices, the T1, for these large scale devices, you can see that these error bars are huge. So we see a lot of fluctuations in this figure of merit, which is generally bad. So now this is looking at a few. I want to move through this rather quickly, but the main story here is that if you look at qubit frequency, which is on the y-axis, and time now in hours, the color here tells you a sort of proxy for the coherence time. And you can see that there are these white regions, which are the really bad things we want to avoid, that move a bit as a function on the time scale of hours. And in particular, like this one here is right near zero detuning. So if a qubit is parked right at this frequency, its coherence essentially goes to nominally zero. It's a really bad problem, and they're very hard to deal with. So in 2021, as a postdoc, we did a rather simple thing on some level, but we replaced most of these superconducting circuits with tantalum instead of niobium. This was really inspired by Bob Kava, who's spent his whole career studying a lot of superconductors, who essentially said, why the heck are you all using niobium? Niobium has a ton of nasty oxides that are uncontrolled. You should use tantalum instead. And when we did that, we basically just did this relatively simple material swap. Now you have to play some games to get the right species of tantalum, and we cleaned up these devices a lot, but more or less we replaced one material for another, and we saw an order of magnitude increase in the coherence time. So now this was state of the art at the time. We're approaching a millisecond coherence, and this same team at Princeton now can consistently get over a millisecond T1. Why that's important is, like, a millisecond coherence time is very good when you consider that gates in the system are tens several tens of nanoseconds for 2-qubit gates. But now this is pretty universally accepted that a lot of groups use tantalum. They see a lot of great results from it. When we first published this work, the question is, why exactly is tantalum a better material platform than niobium for these superconducting circuits? The first hypothesis that I think is pretty widely understood is that tantalum grows a very thin, very stoichiometric oxide. So there's like one type of oxide. Now this is TEM image where you can see the oxide here, and this is tantalum. That's very well ordered, and I think order means that you're not going to have structural disorder that gives rise to certain types of defects. There's a lot of engineering you can do to treat these surfaces, to try to improve the performance of these devices. But generally, there's a lot of intuition from a material standpoint, but there's not a lot of clear understanding of exactly why. Like, what are the defects that we're reducing to change these properties? So the more fundamental question is, like, what are these defects, and how can we design materials from sort of a ground up perspective? And one of the problems with doing this kind of engineering is that we typically build the devices we ultimately want to measure, which are qubits and resonators. But this takes many steps of fabrication. You have to package them up, wire bond them, cool them down in a dilution refrigerator. And then, and only then, do you get some sort of useful data, which is you measure coherence times, and ideally maybe you modify the circuit a little bit and see how these defects move around. Or you change the temperature in the case of resonators, and you can see different populations. And you can build a model that says, hey, I think I have this kind of density of these defects. There's no sense of what they are. And furthermore, the problem with these measurements is they're very small bandwidth. These are narrow band objects, like they're high Q resonators. And they're also very local. And so it's very hard to identify which interfaces defects are arising, or are they in the bulk? Are they in these junctions? All of these things are very hard to disentangle with qubits and resonators, and has been sort of state of the art in the field. So instead, I started out a new lab, and I said, I was trying to get more information from these measurements. And so instead of making what everybody else makes, qubits and resonators, I thought, why don't we try something kind of simpler, which is just build a 3-dimensional waveguide with a really nice high-pass filter property, where we basically have a more or less flat transmission from 3 gigahertz up to at least 6 gigahertz, and I think we can go higher than this as well, and then just shove an actual material into this waveguide and just directly probe the material. And so the reason why this is innovative is, one, it's very broadband, which means we can capture defects over a huge spectral range, certainly compared to a narrow band probe like a qubit. Now, you can tune qubits around and things like that, but like, it's still only locally interacting with TLSs near the actual device and near in frequency. So what's cool about our approach is this is entirely modular. You just slide a material in, you cool it down, you can get a nice spectral response, and then swap it out, process the material, do something different, and measure it again. So that allows you to do these longitudinal studies where in principle you could measure this sort of spectroscopy approach at every stage of fabrication to learn about how these defects change as you move through fabrication. So I mentioned I'm going to be quick. So like, here's the high level picture. Is we mount these samples, we apply a pulsed monochromatic drive. So we apply a between 20 and several hundred nanosecond pulse. That pulse mostly moves through the sample, but it gets absorbed by defects at all these different frequencies. Now, because it's a pulse, we dress all these other defects, and then after we turn off the pulse, we see the sort of ring down and the decoherence of these defects in this polychromatic emission that allows us to back out what the frequencies and other properties of these defects are. So in the interest of time, here's the rub. This is that pulse as a function of frequency. Now we're watching as a function of time of an empty waveguide. Now this is an empty waveguide with sapphire. This is all at room temperature. So you see the pulse come through and you see essentially nothing. This is all electrical noise. You see sort of nothing after the pulse. Now this is what happens when you cool the thing down. In particular, what I want to highlight is this is our sapphire sample at 10 millikelvin. It actually is, we start to see the spectral response of a bunch of defects, but it's pretty quiet. Now, and this is 430 micron thick sapphire sample. This is what happens when we deposit 2 nanometers of ALD grown aluminum oxide. So we see a huge spectral response. So there's a bunch of defects that are in this material. And in terms of a volumetric difference between the sapphire and this added aluminum oxide, it's roughly about 10 to the minus 6 change in the same exact atoms, but deposited in this sort of disordered way. So we gain a lot of information by looking at the amplitude response, but we also can see that actually if we take the Fourier transform of the phase, we get these really nice characteristic V's. And those V's tell us exactly where they are in frequency. Now I'm running out of time and I want to make sure there's time for questions, but this technique allows us to identify spectral peaks that are very clear in high SNR. And in particular, we estimated that there's about 84 of these defects within a gigahertz of frequency, at least within 4.1 to 4.6 gigahertz. These also move around as a function of cool down, but the main thing for this audience, the conclusion I want to get to, is that this approach allows you to probe a bunch of different materials over a pretty wide frequency range. The FFT of the phase of this ring down response allows us to identify unique spectral peaks that correspond to the emission of individual, like atomic scale defects. And what I'm excited about, especially with this audience, is learning how to apply this to other materials and defects. So now you might say, like, what about metals? It turns out we get equivalent information from transmission and reflection. So we can sort of bounce this pulse off of a material and gain some of the same information. We've been exploring some other materials, like this is indium phosphide from a collaborator, Javad Shabani at NYU. We see all these defects in these materials. The really big open question that I want to pose to this audience is, are there materials and devices that you all play with, ideally at frequencies close to what we're probing, where potentially a cryogenic probe where we really get a lot of specificity about the defects and their properties, at room temperature, my hunch is that these will affect the property of these, say, room temperature devices. That's kind of a pie in the sky goal, and I'm really curious to collaborate with some of you to try to address this problem. Finally, just a little bit of a plug for, I just started a podcast that's like supposed to be for a very general audience, where we talk about what science is like in the lab. It's ideally not very technical, and you should check it out. And so I'm trying to stay on time. So here are my conclusions, and look forward to taking questions, or feel free to reach out if you have some materials you want to probe, or if you'd like to sort of work with us on this science. And yeah, hopefully that's a good amount of time and we can go to questions.
Yeah. Thanks, Matthias. That's great presentation. And we have quite a bit of time for questions. For those of you online who want to ask a question, you can ask your question using the Q&A or the chat option. Type in your question and we'll endeavor to get that answer to you live. But if we don't get to it, we'll take it offline and we get back to you. So Matthias, if you can put your, I think I'm very much interested in the podcast as well. If you can sort of put that in the chat as well, folks would be able to.
Absolutely.
would be able to do. Although, so I have, while we're waiting for the audience to ask their question,
Yep.
my first question is, which is really with a lot of capabilities that universities and companies have in general. What is the path? How does one get involved? How does one come through? What portal do you have that somebody can say, hey, we would like to introduce this material and get that testing going on or whatever?
Just send me an email, honestly. Like, if I would love to kind of have a good, obviously you wouldn't reach out to me if you didn't have a good reason why you'd want to do this kind of testing, but we developed this technique. I want to sort of show how useful it is, especially in a broader class of technologies like semiconductor devices. And if we can bridge this sort of cryogenic probe, which I think gives you a lot of resolution and a lot of interesting probes of defects that still ought to exist at room temperature, but are probably very thermally excited. But my feeling is that's potentially a source of loss for something like a transistor, which also operates like in similar frequency range. So the answer to your question is send me an email, and if you have some devices that we could write a paper about ideally, that would be great. But I'm happy to measure materials and devices from people just out of curiosity. Like if we get a huge backlog, then we'll have to be pickier. But I just want to sort of utilize this tool for science and engineering, and sort of expand the scope beyond just this quantum computing application.
Is there talking about material, and is there a limitation to the materials handling, or at this
Not
moment
really.
it's wide open?
It's wide open and modular. Like, we can handle, we're not going to be running 300 millimeter wafers, but we're going to be able to measure rather large devices, but we can also measure small devices. Like, we're talking about things on the order of like several inches to scales of like 10 by 10 millimeters. That, it's a kind of a tiny thing in a big volume, but it's very flexible. Okay. And then, as I said, like metal layers, like one of the things we're going to do next is measure some tantalum and its oxide. The metal, you can't obviously put it in the middle of the waveguide. You're going to get a lot of reflections. But if you sort of just take half of the waveguide and put the sample on the bottom, it should still interact with the surface oxide in reflection, and we should get equivalent information from that. So that expands it to metals, dielectrics, other semiconductors. Like we can really measure a lot of different materials and devices. Yeah. Without the need for packaging, which is, I think, one of the big pitches. Because right now, you do a fab run, you wire bond it, you package it, you put it in a fridge, and then that's it. Your best case scenario is you are reproducible enough in your fab that then you can tweak one thing and hope to see a change in coherence. But it's, again, you're throwing out a lot of data that's there. So we get a ton of data, and it's very flexible is the main pitch.
I'm waiting for, I don't see any questions at the moment online, but I have one more question, if I can be selfish here. Sure. Is that, so you mentioned something about the waveguide that you built, the 3D waveguide. What kind of limitations is there for that waveguide?
Not much. I mean, one of the things we're slightly worried about is currently that thing is made out of aluminum, so it's going to have a native aluminum oxide on it. That's kind of a baseline that there will be two less defects in that waveguide. So that's one thing to think about. But it'd be nice to have it be superconducting. If we make it bigger, we can get down to like a gigahertz. I don't think we're going to do like megahertz scale, but in principle, you can scale up to a bigger waveguide and push the frequency down. We can also, we can measure a wide range of frequencies, but in terms of the waveguide itself, it's actually really, really simple. It's actually just like an SMA coax to 3D waveguide adapter. So it's a really nice, it stays like 50 ohm impedance, and then we just convert it and then convert back to a cable, and everything is pretty easy.
That was my next question. It's like it's like a connector approach or something like that. Or so you answered that question, so
yeah.
Well, appreciate the presentation. Very fascinating. I encourage all the folks who are online and folks who get access to this recording later on, get in touch with you. If Matthias, if you don't mind, put your email in the chat line for everybody to see. So that way you can get in touch.
Absolutely.
With that,
hope everyone has a good long weekend. I have to drop, unfortunately, but
no problem.
You all stay around for the talk, and
absolutely, no problem.
Appreciate it.
Great, thank you very much. All right.